Hey, welcome. In this video, I'm going to go over a more complicated multivariable chain rule question. It's come up on multiple past midterms. It hasn't come up on mine, but it's usually tested whenever you are dealing with multivariable chain rule on a term test. So I'll read out the question first, and then we'll get into it. So suppose Z has continuous second order partial derivatives, and let x equal to 2s plus 3t, and y equal to 3s minus 2t. We then want to use chain rule to find an expression for this right over here, partial squared z over partial s squared, which only involves f sub xx, f sub xy, and f sub yy. So first, what we want to do is rewrite this as something that's more, that's something that we can really work with, or something that's easier to recognize at least. So partial squared z over partial, over partial s squared. We can rewrite this as partial over partial s of partial z partial s. From here, we can then apply chain rule. Again, keep in mind that we don't know what z is, so we can't directly compute this. However, we can use chain rule to expand it and eventually express it in terms of these right over here. So first, let's do that. Or out here, I'll write this on the side here. So we know that partial z, partial s. Again, you can imagine the kind of tree or dependence tree. So in this case, we again know that the general expression for this is partial z, partial x, times partial x, partial s, plus partial z, partial y, times partial y, partial s. The great thing here is we have what x and y are equal to. So we are actually able to simplify this a little bit, which avoids the use of product rule instead later on. So in this case here, I'll quickly compute partial x, partial s, and partial y, partial s. So partial x, partial s. This right over here, we're just taking the derivative of x with respect to x, s. Sorry, so just 2 in this case. And then partial y, partial s. Again, s is your variable, so in this case, it's just equal to 3. So from here, we can then simplify this expression down just a bit. Again, partial z, partial x, we still do not have, and we won't have, but we'll make use of it in order to actually answer the question. So this is again being multiplied by partial x, partial s, which is 2, but I'll just write that out front. So you got 2 times this. Yes, 2 times this plus, and then same idea here, except this is a 3 now, so 3 times partial z, partial y. Okay, with this in mind now, we can proceed from here. I'll actually move this down just so we have some more space to work with. So again, partial over partial s still stays, but now we can replace this inner function with what we have over here. So 2 times partial z over partial x plus 3 times partial z partial y. Okay. The next step is to apply the linear property of the derivative, or linearity, meaning we can apply this, I'll kind of think about distributing it effectively. So that looks like this. So again, because it's a constant, we're able to also just move it out. So technically it would be partial over partial s of this entire thing, but we can move the 2 out front. So we get 2 times partial over partial s of partial z partial x plus 3 times partial over partial s of partial z partial y. Okay, this is the step where things get a lot more complicated, honestly, and do replay this part if needed. I'll try to explain it as clearly as possible over here on the side. So if we just take a look at this specific expression right over here, notice what's happening if we rewrite it a little bit. And I think it actually is a little more clear if I use this. I'll do both of them. So first, we'll rewrite this over here. Okay. So partial z, partial s, we can rewrite this as partial over partial s of z, right? Which is, again, the same thing as just writing f here instead, but I'll just use z to stay consistent. And then doing a similar kind of thing on the right side as well, we have partial over partial x of our function z times partial x partial z, or sorry, partial x partial s. And then plus, I can't move anymore, that's fine. Plus partial over partial y of z times partial y partial s. Right, so again, notice that these two expressions here are identical, they're equivalent, especially if it's just a different way of rewriting it. But after we keep this in mind, this part over here becomes a lot easier. So in this case, if we did plug in, because again, we do know what these expressions are equal to, so we'll just write it similar to that case there. Okay, so again, this is equal to 2 times partial over partial x of z and then plus 3 times partial over partial y of z. And then from here, this is where you have to do a bit of visualization. This z here is a function of x and y. Partial z, partial x is also a function of x and y, even if y may or may not appear. So what we're effectively doing is we're plugging this right into here, wherever you see a z, and that's the kind of trick here. So instead of z here, we're now going to replace it with partial z, partial x, and then later on partial z, partial y. And then that's where the kind of confusing stuff. Like for me, I personally memorized it, but I only recently actually learned how it actually works out. But yeah, we'll make use of that. So here, in this case, we actually won't make too much use of this. I'll just try to focus on this part over here. So for now, I'll take this out. But we'll focus on this right over here. So we have 2. And then here I'm just going to use big brackets just to keep things clear. Actually, are big brackets necessary? No, I don't think they're actually necessary. Well, we'll just keep going like this. So again, we imagine partial z, partial x here, meaning we just replace all of that over here with this. So what that then gives us is 2 times partial, right in brackets. So partial over partial x of, yeah, maybe square brackets would be useful, but it's fine. Partial over partial x of our function, so partial z over partial x. Again, and we're multiplying this by partial x partial s, which again is just equal to 3, but I'll rewrite that in the next step. And then, so that's again just this part over here. We still have this part over here, so partial y of partial z partial x times partial, oh, this should be partial x partial y s partial y partial s. Exactly. Okay. So we're not quite done yet. This is only half of the step. So this is again just replacing this or rewriting it using this right over here. That's the key part. Okay. And this should be a plus. From here, we then just apply the exact same thing, but over here now. So plus 3. So I'm gonna get tissue. Okay. Yeah. So same idea over here. I'll go through it faster this time. We're again just plugging in partial z, partial y into here, wherever you see as z. So this then becomes partial x, partial x of partial z, partial y times partial x, partial s plus partial over partial y of partial z over partial y times partial x, or partial y, partial s. Okay. Again, replay this if needed. This is the more difficult step of this question. Rewriting it here up to this point is pretty simple, quite frankly, but this step right over here is what usually confuses people. It's what initially confused me. But after you express it like this, it becomes a lot more clear. Okay, so now we can rewrite things. So here again, we still have 2. So usually you again still need to remember your basic algebra skills. So again, remember to keep brackets wherever needed. In this case, we can now rewrite this as partial squared z over partial x squared. So hopefully now you kind of see where the f sub x, because again, this right here is the same thing as f sub x. So hopefully you see where that's now coming in. And then partial x, partial s, we again know is equal to 2. Partial over partial y of partial z, partial x is just partial squared z over partial y, partial x. And then partial y, partial s, we again know is equal to 3. And let me just check to make sure. Yes, okay. And then we have 3 times the following. So partial x or partial x, partial over partial x of partial z over partial y. We have this is equal to partial squared z, all divided by partial x, partial y. Again, partial x, partial s is equal to 2. And then finally over here, this right here can just be expressed as partial squared z over partial y squared. I'll rewrite that, partial squared z over partial y squared. And then this is all being multiplied again by partial y, partial s, which is equal to 3. Okay. So again, please, for the third time, do replay this part if it doesn't make sense. But this right here is the key step. Everything else is just direct computations and just understanding the notation. Okay, so now we can expand. So again, just distributing this 2. So we have 4 times partial squared z over partial x squared. Plus, again, 2 times 3, which is 6. So plus 6 times partial squared z over partial y, partial x. And then here we have 3 distributed into here. So 3 times 2 is 6. So times 6 times partial squared z, or partial squared z over partial x, partial y. And then 3 times 3 is 9. So plus 9 times partial squared z all over partial y squared. Okay. And here is effectively the final part of it. We're almost done. Notice we do need everything in terms of fxy, fxx, and fyy. In this case, notice the assumption that we had here. We assume that it had continuous second order partial derivatives, meaning we can employ Clairaut's theorem, meaning these two right over here are actually equal. So we can then rewrite this as in terms of f. So this is equal to 4 times f sub xx. Again, these two here are equivalent. Plus 6 is 12. So 12 fxy. And then finally, plus 9 f sub y. Again, these two here are equivalent. And that's how you do it. So pretty complicated at first, but once you do again understand that this step and you're careful with the computation, the question doesn't become that difficult. It's not that intimidating anymore, but again, review this part over here. The main takeaway here is that you can rewrite the typical chain rule. I believe this is either case 1 or case 2. It doesn't really matter. They're basically the same thing to me. But you rewrite it in this form over here, and then it becomes much more obvious. It's very similar to, if you do recall, parametric equation derivatives. The way you find the second order partial, it's a bit confusing, but when you rewrite it, it becomes more clear. Exact same idea here. Like these two statements are equivalent, but once you write it like this, it becomes immediately clear that you must expand this inside, like this part over here, it expands into this, which again that tends to be the more confusing part. Okay, perfect. Thank you for watching.